This is watch 4, 5 magnets. So the purpose of this lab is to use a magnetometer to determine the value of the magnetic moment of a bar magnet and to write a code that visualizes the magnet's magnetic field. So for the fundamental physical principles, we'll be using the magnetic field using the Biot-Savart law, and we'll also be calculating the magnetic field versus the distance for the bar magnet by finding the values of N, K, and U using the following equations. And then for the introduction, for the main results, we found that the code will calculate the magnet's magnetic dipole moment. And when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component of the magnetic field decreases. Assumptions. Assume that the x-axis is defined by my magnetometer app points along the width of my phone, the y-axis points along its height, and the z points out of the screen. Only the bar magnets is acting on the experiment location, not other magnetic fields or electrical devices. In other conditions, the phone was aligned to face magnetic north. The magnetometer cell phone is a system, and the bar magnet and Earth are their surroundings. So we make experimental setup, finding the magnetometer sensor. We align the magnetometer app with the Earth's magnetic north-south axis. We then have to find the magnetometer sensor in the phone. So first we have to use the magnetometer app. The meter sticks, a bar magnet, and tape. We're going to put a piece of tape on the phone, and the x component is at its maximum, and the y component is at its minimum. Then we have to rotate the phone 90 degrees to put a piece of tape when the x component is at a minimum, and the y component is at the maximum. And the intersection location is where the magnetometer sensor is. So then we have to record the values, but in order to do this, we still have to finish setting up. We have to find a distance from the magnet to the sensor that makes a magnetic field with an x component magnitude of B field of 20 UT, represented as R20. We then have to record the distance M and B field T in the Excel spreadsheet provided, and then we have to repeat this 3 times for R20, R70, R120, R170, and R220. And then we have to repeat this for off-axis measurements. We have to use a second meter stick to measure the D perb by Earth, Bx by measured, and Bz 3 times, and then we have to correct the By values. So these are the experimental results. So first we have to find the constant n and k. We have to use a line of best fit of the LMBx and LNR graph that we used in the previous slide, where we found that n equals negative 1.7, and the intercept LMK equals negative 13.928, so that k equals e to the negative 13.928. Then we have to calculate u, the magnetic moment, and we found that r equals 0.1034 using the BNet and the equation above, and we found that u is 6.1. Similarities and differences in results. So the experimental value of the B field is the following right here, while the calculated one is a little bit different. So for the code, first we have to write down the constants, then we have to create the magnet at the origin, then we have to use a function for the magnetic field. Then we have to visualize the magnetic field on the axis and perpendicular to the axis. We then created arrows on the axis, as can be seen here, and then create arrows perpendicular to axis. Right here, we created 4 to be perpendicular and 2 on the axis. And then we have to visualize the magnetic field at a 45-degree off angle, and we also created an arrow here to represent the magnetic field at 45 degrees from the axis, which has to do with the second part of the experiment when we get to the 2 meter sticks. This results in this kind of diagram where we see that the magnet is the gray cylinder, the on-axis magnetic field is the orange, arrows of perpendicular magnetic field is the cyan, arrows in the 45-degree off angle magnet is magenta. And here we have the values for the B field. And so then for the what if I hadn't oriented my experiment to compensate for the magnetic north? If I hadn't oriented my experiment to compensate for magnetic north, then the Earth's magnetic field would have affected the x and y components of the magnetometer, and this would have altered my results. What if I were to stick 2 identical magnets together and to end the experiment again? How would I expect the measurements to differ? Since there would be 2 magnets, there would be double the magnetic fields, so we can expect the measurements to be double. So possible sources of error are that nearby electrical equipment could affect the magnetic field readings, and there also could not be a proper alignment of the magnetometer with the magnetic north before starting. And in conclusions, we found that our phones have a magnetometer chip that we can use to determine the magnetic field of a bar magnet. We can use GhostScript to create a model showing the magnetic fields with arrows, and we learned that the actual and experimental B field values differ.